What's up, calculus students? Let's go ahead and start reviewing for our midterm. We'll start with reviewing Unit 1, which is on limits, continuity, and asymptotes. Three kind of separate lessons. We also reviewed trigonometry, which I'm not going to bother doing. Limits is when we started talking about not really plugging in the exact value, but plugging in something a little bit less than or a little bit more than a value. So if I said, what's the limit as x approaches 2 from the left, you'd be thinking about plugging in 1.99999. If you have a 2 plus, you're thinking about plugging in something just a little bit to the right of things. So we're not really plugging in 2, but we're going to get a value that's infinitely close to what we would get when we plugged in 2. We're just going to make sure we plug it in or look at the right thing. And if this equals this, then we say the limit exists for 2 in general, where we don't have a letter. So don't have a plus or a minus. So for example, graphically, if I had this situation going on, I would say as x approaches 2 from the left, I'd be using this y value, whatever it is. Let's say it's 3. So this left-hand limit would be 3. If I plugged in 1.9999, I'm going to get something very, very close to approaching 3. If I plugged in 2.001, I'm going to be just to the right. I'm going to be approaching this y value that's -2. If the left-hand limit doesn't equal the right-hand limit, then we say the limit in general does not exist. So this does not equal that, which means the limit in general does not exist. Limits don't exist at jumps or vertical asymptotes. The other way we asked you these limit questions is typically with piecewise functions, where we'd say f of x equals, x plus 2 for x is less than 2, and then like x squared. That's a bad one. Let's do x cubed minus 4. X is bigger than or equal to 2. And this is when, well, maybe let's make this 3. This is where the left-hand limit, if I'm plugging in 1.9999, I'd plug it into the top piece, and I'd get something that's close to 4. So I'd say the left-hand limit is 4. If I ask you for the right-hand limit, I'd be plugging in 2.001. Well, I'd be plugging into this piece. This is the piece we're using for x is bigger than 2. So I'd get something close to 8 minus 3, which is something close to 5. I'd say it's 5. The left-hand limit does not equal the right-hand limit. Limits don't exist. We'd have a jump, okay? Continuity, to ensure things are continuous. The limit at a certain value of a function has to equal the function value. So, for example, for limits, if you have a hole, there is a limit. If I look to the left and right of 2 for this hole, the left-hand limit would be approaching this y value of 3. The right-hand limit would be approaching the y value of 3. So this limit would equal 3. But in this situation, I don't have a function value. It's undefined. So since there is no function value, we're not continuous. Let's say we had a function value as elsewhere. We're still not continuous. We got to make sure that we have limits and function values everywhere. Typically, functions are continuous. We always check to see when denominators are equal to 0. That's an indication that we have a discontinuity. If there's a piecewise function, you want to make sure your pieces meet up. Okay, but this is the definition of continuity, is limits and function values agreeing. And then we have asymptotes. There's 2 types of asymptotes. We got vertical asymptotes. Vertical asymptotes are when at a certain value, you'll get like a number over 0. And we might want to look to the left and to the right to figure out whether we're trending towards positive or negative infinity. Now, vertical asymptotes, different from vertical tangents. Vertical tangents are when our slopes are undefined. Vertical asymptotes are when our function values are undefined in such a way that we have a number over 0. We call that an infinite discontinuity. Remember that if we get 0 over 0, we have an indication of a hole or a removable discontinuity. Remember, holes have limits. If you're asked to find the limits, you would need to kind of factor and try to remove the hole and remove the 0 over 0. Numbers over 0, vertical asymptotes. And then finally, a horizontal asymptotes is when we are looking at plugging in infinity. When you look at plugging in infinity, it's all about who's going faster, who's going slower. And we can think about fractions, and if the numerator grows faster than the denominator, what is happening to each subsequent fraction? They're getting bigger. So faster over slower, we get positive or negative infinity. If we got things flipped and it's slower over faster, flip everything, we would be approaching 0. You have to figure out which kind of infinity it is. If we have a slower over faster, again, you're plugging in infinity for x. This is where we cross out things because we don't have to worry about them. Slow over faster, we're approaching 0. And then same over same, you'll be able to figure out, oh, this stuff cancels. We will have whatever coefficients we have. Very quickly for horizontal asymptotes, don't forget exponential functions like e to the x. As x approaches infinity, it's super fast. But as x approaches negative infinity, it'd be like 0. It's the slowest growing function. It'd be 1 over e to the infinity. It would be not even slow, it'd be 0. Okay? Order things, remember logs are the slowest going function. So if we were talking about as x approaches infinity, slow to fast, we have no growths, which are just numbers. We have no growths, which are like sines and cosines. Those are no growth. Then we have x to powers. Square roots are slower than x squareds. Then we have, before that, the log function, which is the slowest growing function. Grows slower than cube roots, grows slower than square roots. So logarithmic functions, then x to powers. Then we go into numbers to x powers. But if we go to negative infinity, then this guy goes to be the no growth. So just keep that in mind. Okay, that's a good little overview of Unit 1. Let's do the questions. I'm going to do them really quickly. I'm not going to kind of explain. There is no limit at B. Was you have a jump, the left-hand limit's 2, the right-hand limit's 1. There is a limit at A. This is true, and the limit at A is 2. To the left at 1.999 and 2.001, we were approaching 2, so we're good. Left-hand limit does exist. The right-hand limit does exist. However, they don't equal each other, so this is why we get 1 and 2 only. I would need to plug in to the left of 2 and to the right of 2, so I'm gonna have to look to the left of 2. When I plug in something to the left of 2, I would be plugging it into the log x, so I'm gonna get something close to the log of 2. It's like the log of 1.9 repeated, which is essentially the log of 2. Then if I plug something into the right of 2 into my function, I'm going to get something close to 4 ln 2. Again, I'm plugging in 2.001, which is why I'm plugging into the bottom piece. This does not equal this. The two limits don't agree with each other. The limit does not exist. Okay, pay attention to the positive infinity. Here we go. X to any power, as long as it's a positive integer. It could be 1,000, it could be 2,000, it could be 1,000,000. Eventually, we will have e to the x grow faster / take over / go to infinity. So this is a slower over faster situation, and slow over faster, we would keep trending towards values that are getting closer and closer to 0. Part of asymptotes are canceling or not worrying about slower growing pieces. So if I'm plugging in infinity, This is insignificant. I'm only am allowed to do this if I'm plugging in infinity. I just care about 3n squared over n squared. Well, that growth cancels, and we just get this number 3. Another horizontal asymptote. It's not a horizontal tangent, it's a horizontal asymptote. Make sure you understand we're not looking at slopes, we're not looking at derivatives, we're just looking at the function. And here we have 4n squared over n squared, which is 4. We have a horizontal asymptote at y equals 2. Well, if I plug in infinity into this, I should get 2. Well, if I plug in infinity, I don't care about that and that. I get that A has to equal 2. I have a vertical asymptote. This isn't a vertical tangent, it's a vertical asymptote. Vertical asymptote, you should be thinking number over 0. If I plug in -3 as an x value, I should be getting a number over 0. Well, the top is going to be just something. It's going to be a number. The bottom will be 0 if c is 3. 3 plus 2, 5. Let's say f is continuous. Well, look at this situation. If I plug in -2, I get 0 over 0, which means I have a hole. To fill in said hole, I'm going to need to find the location of the hole. And I'm going to need to make sure we have a point at this location. Because if I have a hole, okay, well, where is the hole located? Now my function is continuous. So to find the location, well, we want to try to plug in -1.999, -2.001, but I'm not able to right now. But this is when, if we have it as a factored form, we will be able to cancel. When I plug in -2, be able to cancel these zeros. This 0 over 0 will cancel, and I get -2 minus 2, which is -4. So this must be true. This is the hole's location at -4. My x-axis has got to be up. All right, now we got a piecewise function. We got to make sure the pieces meet up. So we're going to be looking at the one-sided limits at 0, at 1, at 2, all of these x values. So I start with plugging 0 in here, I get 0. If I plug 0 in here, 0. So 0 is continuous. So 0 is continuous. Now let's try 1. I get 1 and 1. So 1 is continuous because the two pieces meet up. If I plug in 2, 0, -1. All right, 2, we are not continuous. So it's just got to be C. I already checked 0. Oh, I forgot about the intermediate value theorem. Intermediate value theorem says if your function is continuous, you have 2 points, you got to pass through all of these y values at some x value. It's like, do we have to have a 0? Sure. If you go from a negative y value to a positive y value, you're going to cross these zeros somewhere. If f of x must equal 1/2, and it must have at least 2 solutions, if k, well, if you think about this, if you got the point 0, 1 and the point 2, 2, to get to this point 1/2 twice, we're going to have to drop below 1/2, which means having this y coordinate of 0 somewhere, then we'll definitely have to drop below it and continue up above it. If this limit equals 7, all we know is that we have a limit. Do we have to be continuous? No. We're not certain that this function couldn't have a hole at 3, 7. So we don't have to be continuous. Unless we have a slope. Well, we don't have to have a slope if we don't have a point. Must there be a function value that equals 7? No, it doesn't have to be. Okay? Good review of Unit 1. Limits, continuity, asymptotes. On to Unit 2.